Hi, Algebra 2. In this lesson, you're going to be using what you've already learned about exponential and logarithmic functions to solve equations that have them in it. Here we go. First thing we have here are some options we have when solving equations with exponentials or logarithms. Right here, these two things are the same. So basically, if we have just x equals y, or like two things on each side of an equal sign, we could raise both sides of that and put a base in of really any base we want, and then raise that to the power of x and the power of y. And our function will still be true. It's like doing the same thing to both sides of the equation. Similarly here, if we have something like a equals b, something on both sides of the equal sign, we can take the logarithm of both sides if we think it's going to help us solve the equation. When I look at this first example right here, the first thing I notice is that 9 and 27 are both products that we get when we take 3 to a power. So I'm going to rewrite these as 3 to a power. So 9 is 3 squared. That's going to be raised to the 8 minus x power. 27 is 3 cubed. That's going to be raised to the x minus 3 power. And now I'm going to remember that when I take a power to a power, we multiply. And so this is 3 to the power of 2 times 8 minus x equals 3 to the power of 3 times x minus 3. In order for both of these sides of the equal sign to be equal, these exponents need to be equal. So I can really just look at this part. 2 times 8 minus x has to be equal to 3 times x minus 3. And I'm going to figure out what x is here, and that's going to make both sides of the equal sign the same. When I solved this equation, I ended up with x equals 5. So again, that means that when I put that in here, it's going to make both sides of the equal sign the same. In this example, 4 and 5, I'm not going to be able to write as numbers with the same base to a power. So instead, we're going to use the rule that says that we can take the logarithm of both sides and then use properties of logarithms to solve this, which means this exponent, x minus 1, can come out front, just like we saw in lesson 4. And then I'm left with this. I can divide both sides by log of 4. And end up with x minus 1 equals log of 5 over log of 4. And then I can just add 1 to both sides. And so I end up with x equals the log of 5 over the log of 4 plus 1. And if I want to estimate that as a decimal, using a calculator, I would find that this is approximately 2.16. When we rewrote this one using the same base of 3, the equation ended up being pretty simple. Then the exponents had to be equal, and I got x to be 1.5. I rewrote this by taking the log of each side, and using my properties of logarithms, I can bring that exponent out front. And then I'm going to divide both sides by the log of 7. And at this point, I would either multiply or divide both sides by -1. So that I get a positive x, and that would be x is going to equal the negative log of 21 over log of 7. As a decimal approximation using a calculator, this would be -1.57. Okay, I wrote our general exponential function over here for reference. Our initial bacteria is just going to be 1. It's kind of hard to tell in this problem, but it's just 1. And then it's going to double, so that's our growth factor, every hour. And we know that that's going to be x. Now we're wondering, when is it going to be 1,000,000? Or when is it going to exceed 1,000,000? So I'm going to rewrite this as 2 to the x equals 10 to the 6. It's going to be easier to write it with that exponent, because now you can use your rules of logarithms to solve for x right here. Here I took the logarithm of both sides, and then I rewrote it bringing that x out front using the properties of logarithms. This side of the equation can be simplified. Remember, this is base 10, so I'm thinking 10 to what power equals 10 to the 6. So my question mark there is going to be 6. That side can just be simplified. And then I'm going to divide both sides by log of 2. If I use a decimal approximation, I would get x to be 19.94 hours. That's when it's going to equal 1,000,000. We wanted to know when it's going to exceed, and in real life, we would just round that to 20 hours anyway. So at that point, it's going to be over 1,000,000. This slide is just reminding us that you solve logarithm equations by using the properties of logarithms. This is that property that we said we can take the log of both sides when we have something in an equation, and that can help us solve. When solving these equations, we remember our properties of logarithms, but also just the definition of logarithm, how we go from the exponential to the logarithmic function. Because in this first one, we can just use that definition. We can rewrite this as 6 to the negative 1 power equals 2x minus 1. That negative 1 power kicks it to the denominator. It's the same as 1 over 6 to the first, or just 1/6. And now we have an equation we can solve. I solved this like any other equation. I added 1 to both sides, so I end up with 7/6 equals 2x, divided both sides by 2. One thing to keep in mind is that dividing is the same thing as multiplying by the reciprocal. So it's the same thing as multiplying by 1/2, and I get 7/12 to equal x. Here I used a property of logarithm to rewrite this. Now I'm just going to use the definition. I could rewrite this as 4 to the first power equals 100 over x plus 1. I'm showing you two ways that you could solve this part of the equation. First way is that I multiplied both sides by x plus 1, and you can follow my work here. The other way is just to think through this logically. 100 divided by what is going to be 4, and so this denominator has to be 25. So that means x plus 1 equals 25, so that means x has to equal 24. I rewrote this using the properties of logarithms, and now I'm going to just use the definition. 12 to the first is going to equal x times x plus 1. With a distributive property, I get this. And now I'm looking at this like a quadratic. So I'm going way back, solving it like it's a quadratic, setting it equal to 0. And then I'm going to look and see, can I factor this? Turns out we can factor it, and we would get the solutions of x equals 4, that's one of the zeros, and x equals negative 3. So there's two possible solutions here. We have to see which one is going to work. Here's a note you might want to write down. You can only take the logarithm of positive numbers. So this part right here, if x was negative 3, that is not going to work. That's going to be undefined. The only answer that works here is x equals 4. In this example, I want to use the property of logarithms that allows me to write this as a single logarithm, but this 3 right here is causing trouble, so I'm going to use the property and put it right back into the exponent. Once I've done that, now I can write this as a single logarithm like this, and then remember this is base 10 right here, and I'm going to rewrite it as 10 to the third power is going to equal 8x to the third. So as I keep working this through to solve for x, I end up with 125 equals x to the third. So I'm thinking what number times itself 3 times gets me 125. I do realize that that is going to be 5. However, if you didn't recognize that, what happens here is you're taking the cube root of both sides. So if you need to use a calculator, that's what you would do to get x equals 5. In this one, I wanted to use the property of logarithms with subtraction, and so I had to put this 2 back up here into the exponent. So now I have it rewritten like this. Remember, this is a base 10. I'm going to use the definition of logs here. 10 to the 0 power is going to equal x squared over 4. Anything to the 0 power is 1. To continue solving here, I'd multiply both sides by 4. I get 4 equals x squared, means I would take the square root of both sides. So I get 2, or plus or minus 2 is going to equal x. However, looking back up here, we can only take the logarithm of positive numbers. So negative 2 is not going to work. The only answer that works is positive 2.